Okay, so thanks for coming to our colloquium. Today we have Martin Rubin from the University of Bern. And you see the title, it's about comets and spectrometry, sorry. And we have Martin Vollwerk, a colleague of his, who will introduce.
Yes, good afternoon, everybody. Okay, our distinguished speaker today is Martin Rubin from the University of Bern, as was already said, where he's now or for a longer time, a senior staff member. So I guess he's stuck there now for the rest of his life. Yeah, yes. He got his PhD in 2006 in physics, and then he had his habilitation in 2015, and now he's a docent at the Physikalisches-Institut in Bern. Not surprisingly, he was on a lot of ESA teams, which I saw on his CV. I'm not going to list them all, but with ESA in Bern, that's pretty easy to be a member of the team. For the rest, he's a co-I on some ALMA projects. That's one of those observatories, and for instance, looking for oxygen and the ratio of oxygen 16 over oxygen 18 at comets, and the not so nicely smelling H2S at comets. So yeah, the fun things that you get at cometary physics. Of course, I met him the first time when I joined the Rosetta team, and then I found that was yeah, very nice person to work with. He was always happy to do stuff. He's the PI on the Rosina COPS instrument. I guess we will hear about that during the talk. And oh, other side. And I guess the Rosina instrument on Rosetta is the instrument with basically the most Nature and Science papers published from what I so gathered. Well, it's somewhere in the top, somewhere on the top of things. And Rosina is famous for the zoo, which will probably also appear during the talk. And looking into the future, which is also already on the screen, he's also PI on Maniac, on which ÖAW is also involved for the Comet Interceptor mission. And yeah, the last thing we can say that he's also known as an asteroid now. He's an asteroid 11811, Martin Rubin, which has a size of 2.75 kilometers, a magnitude of 15.1, and an albedo of 0.257, which is probably significantly larger than the albedo of a cometary nucleus. So you can actually see him instead of the nucleus of a comet. And that's enough nonsense from me, and I give the floor to our speaker, Martin Rubin.
Thanks a lot for the very nice introduction. You know, I hope we're never going to see that asteroid in big. It will make me famous, but that's not the way we want to go. So I'm going to dive right in. The topic of today is neutral gas around comets. And by means of mass spectrometry. And I listed here 3 missions that basically will carry a neutral gas mass spectrometer and visit a comet, or has already visited a comet. And that's Giotto, then the Rosetta mission, and Comet Interceptor will discuss them in the end of this talk. So what is a comet? 2 objects here. Well, you all are well aware what a comet is, but they almost look the same. And we typically, that's actually a debated number, that in a comet about 50% is refractory material. Refractory meaning dust and dirt and organic residues, soot, whatever, may actually not be that refractory, but we'll also get to that. And then, of course, at a comet, 50% roughly is about ice. Different ices, CO2, water, and so on. and we also get to that. And the sun heats up the outer layers when a comet comes close to the sun, and then the ice directly vaporizes. Obviously, comets, we don't really know comets the way they are displayed here. We typically see a comet because of their famous tail. The nucleus of a comet is here somewhere in the middle, of course, much smaller than a pixel on the beamer or a pixel on the telescope or whatever. But the size, because they have such a low gravity, they basically, the ice that sublimates, carries with it dust, blows it out into outer space. And because the object is so small, there's no gravity, and it's basically pushed away by the sun. So you get different cometary tails. For instance, an ion tail that points directly away from the sun, and along the trail is the dust tail. And in the middle, you can get different tails from neutral gases. The size of such a tail can be, large. That's an example, 1 AU. I mean, cometary particles, they never vanish. If you pass by the tail of a comet at 3 AU, you will still find oxygen atoms and so on, or oxygen ions and carbon ions. I think there were comets tails detected out to 3 astronomical units from the actual object. How do the nuclei look like? There's a few examples of actually comets that have been visited by spacecraft. And they are on the order of a couple hundred meters to a few tens of kilometers, the range of comets. And actually what you also see is they have a complicated shape. We'll get to that. Some of them look very much like contact binaries. That's one of the hypothesis that these objects formed by slow merging collisions. And the lack of gravity basically doesn't turn them into a spherical shape. Where do they come from? They come from different reservoirs within our solar system. You see here, top right, our solar system up to Mars orbit. And then outside, further down here, outside of the orbit of Neptune, roughly the Kuiper belt. So comets originating from the Kuiper belt, which is here basically in the ecliptic plane. And as you move further out to 100,000 AU or even further out to the next star, we then basically have the Oort cloud. And what happens is if, let's say, a star passes near, somewhere around close, let's say, to our star, some of these objects, they get deflected from their position, and then they may be entering the inner solar system, and that's when they become a comet. And that a typical comet orbit is elliptic. So most of the time, these objects still spend far away from the sun, and only during a short time when they pass through the inner solar system, some of them return, some of them come only once, tumble into the sun, and some of them may even be ejected out of the solar system. But basically, they spend only a short amount of time in the inner solar system where they lose their material. So comets, they pass by the sun at a limited number of times until they lost basically all their material or their volatile material. And for us, that makes comets very interesting because, as we've seen before, most of the time they're very far from the sun, and even when they become a comet, most of the time they spend in the far reaches several AU at least away from the sun. That's basically when you go to the kitchen and you want to preserve your food, what do? You put it in a deep freezer, and basically the comets are the messengers from the deep freezer of our solar system. And it basically means that with their story of how, where they resided before becoming a comet, is that when we study the material of a comet, we can learn about the material from which our solar system formed. And that basically what makes them interesting. They preserve the material since the formation, especially for me interesting, or for us, is the ices. Comets have been depicted a long time ago. This is the first depiction of a comet. You see Comet Halley here, top right. It's a tapestry from Bayeux, telling the story of the that led up to the Battle of Hastings in 1066. And so typically comets were thought to be a foreboding, well, good or bad, depends whether you look at it from the English side or from the French side, good or bad news, but that's basically Comet Halley here in 1066. This here is the orbit of Comet Halley in 1910. And actually you see the track of the comet here, passing inside the Earth's orbit. You see the Earth passing here in the opposite direction. We'll get to that. And interestingly here, actually on May 18, 1910, the Earth is in the tail of Comet Halley. And this was not very well received at the time, because spectroscopically, for the first time, it was detected that comets carry cyanide, CN, HCN. So, of course, everybody got worried that this is going to be the end of us all when we pass through the cyanide tail of the comet. Well, fortunately enough, fake news, we have enough of that, and of course it did not happen. But still, the next revolution, Comet Halley, returns every 76 years. ESA started a comet mission called Giotto. It's named after the painter of this here of the Christmas story, fitting December, the time of the year. And you see again Comet Halley. And the painting was painted in 1301, which is 3 revolutions after the tapestry that I showed you before. So the Giotto mission to Comet Halley, it passed by Comet Halley on the 13th of March, 1986. And you see here the Earth's orbit and the orbit of the Giotto spacecraft. And you see the comet in yellow. Basically, it has an inclination of almost 180 degrees. It's a little bit less, but basically what this means is that the probe, the Giotto probe, and the comet basically passed each other in opposite direction, which meant that the speeds, the relative speeds, were very big. The relative speeds were 70 kilometers per second. And at these speeds, typically a 1 gram particle of 1 gram mass has at these speeds has the energy of a 2-ton car at 180 kilometers per hour. So you need to have strong or very good dust shields. That, of course, did not prevent that some of the instruments, died once at closest approach at Halley. So it carried a bunch of instruments, and we have here the 2 mass spectrometers that I was not involved in. I was before my time. Yeah.
To allow a quick question.
Yes.
Why did they design this leaf comet in the wrong direction? Why not having a rendezvous the other way?
It's much easier if you take the speed of the Earth basically when you launch. So basically you always launch with take the motion around the sun from so it's it will also be an issue for the Comet Interceptor issue mission in particular for our instrument. Here at least the advantage was that you knew what the encounter speed is going to be. So you design your instrument for an encounter speed at 68.3 kilometers per second, which causes some, but this, well, we'll get to it. So there was a neutron mass spectrometer and ion mass spectrometer. Both of them had contributions from Bern. But in the interest of time, I'm not going to talk too much, or I'm not going to talk about the Giotto mission results, because some of the stuff I can try to cover with the Rosetta mission. But basically, this mission produced something like 20 minutes of data because of the high flyby speed. And actually, some of the instruments, including the mass spectrometer, died at closest approach. So you only got half of the data. You only got the inbound pass and the outbound pass. And then, of course, Giotto went on to encounter Comet Griggs-Kellerup, but then the mass spectrometer didn't work. So these are all reasons to go back to a comet and to do it a little bit differently. And that was the idea of the Rosetta mission. The Rosetta mission, actually, the idea was then to do a rendezvous and to follow the comet and to orbit the comet for some extended amount of time. In fact, it was just about more than 2 years of continuous operation. What was the idea of Rosetta? I alluded to this earlier, is actually to decipher what is the material from which the solar system emerged, and with this, the planets, and with this, ultimately also life. Of course, these are grand goals, and Rosetta did not explain to you where life is coming from, but you see the idea. You have to have grand goals to get such a mission through ESA. And it was, why is it called Rosetta? It's called Rosetta after the Rosetta stone that was found by in Egypt by French troops from Napoleon. And you see a picture here. You can see it in the British Museum in London. It basically has 3 times the same story, once in Demotic, once in ancient Greek, and in hieroglyphs. And because, well, the hieroglyphs were unknown at the time, but the Demotic was known and the ancient Greek, and one knew that the two told the same story, so the hieroglyphs would also have to tell the same story, and that helped to decipher the hieroglyphs of the Egyptians. And that's basically an analogy. Rosetta should decipher the origin of the solar system, the Earth and life, by studying a comet. So the Rosetta mission had a bunch of science goals, and I'm not going to go through all of them, but the ones that are aimed at or where the neutral gas mass spectrometer could contribute. That's on one side the determination of the chemical, well, not mineralogical and isotopic composition of the volatiles. Then how these volatiles and refractories are mixed in the cometary nucleus, and also how cometary activity started, or how it develops. There's also, of course, as a secondary instrument, the mass spectrometry could contribute to, as input, for instance, for the plasma investigations that you were carrying out. So on the 6th of August 2014, Rosetta counted the comet. And you see here an image sequence of Rosetta approaching the nucleus, rotating, and you see the pointing is not yet perfect, so they had to work a little bit. Actually, the comet had vanished out of the field of view, but that soon afterwards got improved. This was about the distance at Jupiter's distance, so the one-way light time or signal time is 45 minutes to go to the spacecraft, and then if you want to do operation, you have to wait 45 minutes additionally to see whether your commands have been executed, which basically means a lot of it has to work autonomous, or you have to give it enough lead time and to take care of that issue. You see here a picture of the comet, and pretty soon it was clear that it's basically a rubber ducky, and it actually helped. It helped us because when people were talking about the neck, everybody knew where to look at. You know, or when we talk about the head. Also, you know, nowadays, or now already 10 years ago, it was cool to make selfies. So Rosetta also had to do a selfie. It was an image taken from the lander, which is was mounted on the back of Rosetta. You see on the back side here of the solar panels, and actually a picture of the comet here on top. Then on the 12th of November 2014, so 2.5 months after the initial approach, the lander deployed itself and carried out a suite of measurements on the surface of the comet. So here a few vital statistics of the comet itself. It has basically the long axis is about 4 kilometers, and then the smaller axis more like 2-3 kilometers. It has a bilobed shape, and it had a rotation period, I'm going to get to that, of about 12.4 hours at the encounter. Also here, the activity, you see the activity was picking up June, July, August 2014. So from, well, milliliters per second, and in the end, it was at perihelion, it was about 100 kilograms per second of material that is lost every second. So the comet obviously gets smaller, and also, well, we'll get to that. It also changed its rotation period due to the outgassing that was speeding up its rotation. Rosetta carried a bunch of instruments. I already mentioned the lander. It had 2 experiments on board and the weight of about 100 kilograms. And on the orbiter, there were a bunch of instruments, optical instruments in different wavelengths regimes. But then there were also dust instruments, dust counter, and also a dust composition measurement doing secondary ion mass spectrometry. Then there's a plasma package containing Langmuir probe. There was an ion electron sensor. There was an energetic ion, well, not energetic, was an ion sensor, and yeah, magnetic field, and so on. And then there was a radio experiment that was used to get the gravity field with high precision. And I'm going to be talking about the neutral gas mass spectrometer called ROSINA. ROSINA stands for Rosetta Orbiter Spectrometer for Ion and Neutral Analysis. And it contained 2 mass spectrometers, 2 different types of mass spectrometers. There is RTOF, the reflectron type time of flight. The same principle is going to be used for Comet Interceptor, and we're going to look a little bit closer into the instrument later. Then there is a double focusing mass spectrometer. It has an electrostatic and a magnetic analyzer, which basically separates ions by mass to charge ratio. And COPS, that was the Comet pressure sensor, measuring the absolute density of the gas surrounding the spacecraft, which means the gas from the comet, but also the outgassing of the spacecraft itself. And basically it measured the gas density with COPS, the absolute density, and the composition with the mass spectrometer when you combine these measurements. How do the data look like? That's a spectrum from the double focus mass spectrometer on mass 28 atomic mass units. And you have a few different species. Silicon, that was actually quite a surprise that we saw silicon. Why would we see a refractory element in the gas phase? It's still not fully understood. The other ones were more or less expected. You have the volatiles. Carbon monoxide is a known species in a comet. Then N2 needs a very high mass resolution to actually detect it, but it was also expected at comets. And then we have others like ethylene, and then also their isotopes Okay, that's very marginal here to it's a log scale here, but you have then also a bunch of isotopologues and other fragments. So how did Rosetta fly around the comet? You see that here in a sketch. Looks quite complicated. Most of the time, Rosetta, especially early on in the mission, was in orbit around the nucleus. This was possible if done within 30 kilometers from the center of mass from the comet. Outside, the gravity field was too small. And it was mostly in the terminator plane. And this allowed to observe the comet and also expose the solar panels full time at the sun. So the 12th of November here, you don't see the orbit, but basically that's when here where the Rosetta deployed the lander, or actually the lander deployed itself. So when you look from an observational geometry, you see here the spacecraft with the instrument deck pointing towards the comet. The comet has a tilt with its rotation axis with respect to its orbital plane or to the ecliptic, which basically led to pronounced summer and winter on this small object. There were also restrictions as to whether you could point the backside of the spacecraft towards the sun, because there were the radiators of the cameras. So there were quite a few limitations, especially once you got closer to the sun. But basically, the instrument deck was nominally pointing at the comet. And so this was a standard, well, for the mass spectrometer, it was an okay orbit. Some people would, of course, have liked to stay, on the day side, or actually it would have been interesting to also pass over the night side. But the spacecraft, even though it had batteries, it was never designed to really stay for a long time on the night side. And actually, we were not allowed to use the batteries, so we could never go into shadow at the comet. So here you see our first measurements. Rosetta coming in here, the dashed line on the axis here to the right gives you the distance. And this was basically the signal measured by the pressure sensor, by COPS. And so you see, you come here from 200 kilometers, early August 2014, here to the close point, and the signal goes up. Then the spacecraft moved away again, the signal goes down again. On top of that, here, that's the spacecraft outgassing, spacecraft losing volatiles that are trapped inside the structure of the spacecraft, from glues, from lubricants, and so on. So this is a major issue for us because, we go there to measure a comet and we don't want to measure the dirt we brought by ourselves. That's cleanliness is a topic for a mass spectrometer. On top of that, you see here the rotation period. It was about 12.4 hours, as mentioned before. The comet, due to the outgassing, it did speed up. So at the end of mission, the rotation period was 24 minutes shorter. So it started to spin up, basically because of the outgassing and its complicated shape. That led to outgassing and spin up of the comet. And so you basically see the heartbeat, so to say, of the comet, which has to do with the rotation of the object and its illumination. You see that here, this is just a computation of the solar elevation angle. So if you have, well, 90 degrees means the sun is directly shining on top of the comet. And this is the viewpoint from Rosetta. So Rosetta in the terminator plane, the sun shining onto the comet is rotating, and this is basically the view you would get from Rosetta. And you can imagine that there are times when you see a lot of illuminated surface, and then there are times where you see only little illuminated surface. And that's basically generating the heartbeat that we've seen before. And it also has an impact on the composition measurements, and you see that here. you see now for two species that were measured. One is water here in blue, and then the CO2 in red, and actually it's also carbon monoxide. So you see, depending on where you look at, you may get more water, you get less water, especially from dark places. You see much less variation in the more volatile species, which probably seep out from regions farther below the surface. And at times, CO2 was even the dominant species, especially when you looked at the backside of the nucleus. And when you project this ratio, CO2 to water, onto the surface of the comet, this is really just a direct projection. And of course, the story will be more complicated. We'll get to that. You see that in this case, it was the northern hemisphere was in summer. That's where you got a lot of the water out, and the southern hemisphere at that time early in the mission was in winter. And if it was in winter, you had much more or a higher percentage of the carbon dioxide coming out from the southern hemisphere. Of course, you see all this complicated behavior. So the typical approach of, just taking the comet as a point source is not necessarily working very well here. For that, okay, that would, you see here an image actually taken from the microwave instrument MIRO. And it shows the water column density, and it shows a strong enhancement here towards the sun of the water. It's basically a similar finding that we just discussed, and very little here on the shadowed part. So typically you need much more complicated models, but this would be another talk. So I'm just gonna refer here to some of these approaches that have been applied to this, from Monte Carlo to fluid dynamics model, also different semi-empirical models. The reason for this is that actually the comet, you see this here, and this is dust. These are dust outbursts and dust filaments that are being basically entrained in the gas. We don't really see the gas here, but it's clear here that the point source approach is not necessarily what you have to do. So if you do a complicated model with different outgassing, that takes care of self-shadowing, that takes care of the complicated shape and so on, then you can go a step further. And that's one work that has been done by Gombi et al., showing the activity from early August here. As the comet picks up, it's given here in particles per second that are being spewed out or sublimating off the comet. That increases here towards perihelion, and maybe 2 weeks after perihelion, it decreased again. And you see an overlay here of different instruments. This is water production rate. So you have Virtis in red. So we have a little bit of that's still ongoing here, why there's this discrepancy. In blue is DFMS, the Rosina instrument, MIRO in black, and these are 2-day averages. And then also from the Japanese Lyman alpha here, shortly after perihelion, what was observed was the hydrogen, and basically using a model, this was turned into a water from which then the hydrogen is produced. This here is an interesting plot. It shows forces on the spacecraft of Rosetta. And for comparison, you have the red dashed line, 1G, gravity on Earth. Then you have the gravity on the comet surface, the gravity at the ISS for comparison. And then you see the different forces that act on the spacecraft, the Rosetta spacecraft. So the main force here is basically, once you get close to the comet here, is the comet central, so the mass. But then you also have the higher orders of gravity orders because of its irregular shape. You see it here in black. Or you have the sun here as a third body, which, you know, when you get closer, you see the decrease here with respect to the force exerted by the comet nucleus. But you can then also calculate the drag force here, and that's the orange one. It's based on COPS. It's a drag force exerted onto the spacecraft because you're basically exposed to gas that spews past the spacecraft. So we talked a little bit about activity. The next thing I would like to talk to you about is the composition. Because, you know, Rosetta was set out to tell us, you know, about all these grand things of where it comes from, how it was formed, and so on. And so basically, our Rosetta story or Rosetta stone is built up of different molecules. And all these molecules tell us a little bit of the story. And the idea here is, if you look at the evolution of the material, we start in the interstellar medium, hot gas that cools, go to the dark molecular clouds where you get lots of chemistry and then the formation of molecules. Then star forming regions where you then produce these disks where also our sun and the planets formed in, then the solar system that forms, and in the end somehow life as we know it got to be. And these are all processes that you know, depend on what is there to begin with, and also under which conditions, what are the conditions, physical and chemical conditions, temperature, the time available, and so on. And so here, when we go to the top left, if we compare, for instance, what we find in a comet and compare this to the interstellar medium, that's an interesting plot here. It shows relative abundances of a set of molecules with respect to methane in the comet. And on the y-axis, it's around an object in the interstellar medium, IRAS 16293. And it's interesting, over many orders of magnitude, you sort of get similar relative abundances if you normalize it to methanol. These are for CHO bearing groups, and this indicates that the chemistry must have some similarity, also the abundances, possibly also the material could be inherited from in the comet that we find in the comet could be inherited from such a stage. It's a little bit more complicated here for the nitrogen bearing species. I mean, there are some caveats to this plot here because with the mass spectrometer, you have issues distinguishing isomers like HCN and HNC, for instance, but spectroscopically you can distinguish them. So the idea here is basically you sum it up for the mass spec and spectroscope. Well, for the mass spec you get it anyway summed up because we cannot distinguish them, and spectroscopically you sum them up. But there are some caveats to this. But this is not something, I mean, this has already been observed earlier on. Dominique Boclet-Morvan has written a paper where they have seen the same behavior with other objects in the ISM and with the Comet tail bob. Another interesting molecule is the O2 that was detected at the comet. Nobody expected it to be present there in high abundances, but it's actually, well, it's probably at this comet, it was the third or fourth most abundant molecule, O2. And also, you see here a plot. It's a very busy plot, but basically the idea here is to just to show you that you have the O2 in black, and you have the water in blue, and you see that they correlate quite well, blue and black. not so much with the CO2 or with the CO, despite that CO2 and CO have much more similar, especially the CO has a more similar sublimation temperature than the O2. But the O2 actually correlated very well with the water. There were several theories of how it would form. Radiolysis did not really work because you don't get that much radiation into the mid-plane, so you have to shovel the material to the edge of the plane and back. There were other argumentation that it could be coming from H2O during the sublimation through this mutation. But recently we have seen that the isotope ratios of the H2O and the O2 doesn't really work or does not really fit, which would suggest that the O2 must have not formed directly from the water, but through other processes, possibly by gas phase chemistry. We also have a lot of highly volatiles. N2CO, I've shown you the spectrum before, but also methane. That suggests that these comets were never really very warm because they're still there. That they cannot have been part of a big object because then you would have heated up and lost lots of these molecules. And one suggestion then is that they formed about 25 Kelvin. There was no neon detected, which means that the neon got lost. However, there are some caveats, and this is shown here, is that you see here on the, that's an example for the carbon monoxide. You have the carbon monoxide here on the y-axis. On the x-axis, you have CO2. Here you have, again, the carbon monoxide, and here you have the water. And here you have, again, carbon monoxide, and here you have a factor times the water density plus some factor multiplied by the CO2 density. And you can basically predict by the amount of CO2 and the amount of water how much CO you will get. What does this mean? Okay. What does this mean? It basically means that the CO2 or these highly volatiles are most likely trapped. They are most likely trapped in the ices. So we found a lot of different species, and that's the zoo that you alluded to. We grouped them in, an old the hydrogen cyanide. These are the poisonous snakes. If you remember the picture with Comet Halley, flying the Earth flying through its tail. The cyanide, you have the funny ones, the alcohols. Then the giraffe here, these are the carbon chain molecules. And the very volatiles, the butterflies here, the molecular nitrogen, and so on. So basically, at this point, this was basically a depiction of how these species, how would they smell, how would they look like, or how would this look like? We were then asked, how would the comet smell? We have a bunch of these species here. And of course, I'd like to give you the short story about this. This was a press release that I'm going to reproduce here. The perfume of 67P is quite strong. With the odor of rotten eggs, that's the hydrogen sulfide, horse stable, that's the ammonia, and the pungent, suffocating odor of formaldehyde. This is mixed with the faint, bitter, almond-like aroma of hydrogen cyanide. Add some whiff of alcohol, or in terms of methanol, to this mixture, paired with the vinegar-like aroma of the sulfur dioxide and a hint of the sweet aromatic scent of carbon disulfide. And you arrive at the perfume of our comet. This went around the world. That's the press that we got. We were in particular proud of this one here. It's from the Swiss farmer, Schweizer Bauer, that the comet smells like a horse stable. So the next, or to finish, I would like to tell you a little bit about the Comet Interceptor mission, in particular because we have a lot of involvement from IWF. Comet Interceptor is intended to launch in 2029, and it carries a main spacecraft that passes at a safe distance from the object that's yet to be defined. So it's a first mission that starts without having a target. And it has 2 probes that will be released just before the flyby. It's an F-class mission, and ideally we would like to fly by a dynamically new comet. That's why we have to be already in space to encounter it, or possibly even an interstellar object. Comet Interceptor has a main spacecraft and 2 probes. One is from JAXA, the Japanese space agency, the B1 probe, and also on the B2 probe. I've marked in yellow contributions where IWF is involved. That's on one side, the magnetometer on B2, and then also on the MANIAC, that's the mass spectrometer on the main spacecraft. The mass spectrometer has, well, first the Comet Interceptor is set out to perform multipoint measurements. That's why it has these 2 subprobes. But also, as I mentioned, to encounter ideally a pristine, dynamically new object. The mass spectrometer will measure volatiles, H2O, CO, the major volatiles. The idea is also to derive the idea, or if the object is active enough to get the isotope ratios. Look for volatiles such as O2, the story I told you before. So we want to see this in another comet. Measure organic molecules and the icy grains. The mass spectrometer you see here at picture, so only the part here is sticking out. The gas from the comet is entering the instrument at a high speed, and then it gets thermalized inside this antechamber. By chance, it may get into the ion source where it gets ionized, and once they are ionized, they get extracted by extraction pulse, a fast one, and then, because they all get the same energy, the lighter ions arrive at the detector first. So you get the light ion to arrive before the heavy ions, and so you can separate them by mass. So, well, how is it doing that? Comet Interceptor, the first thing, it starts together with Ariel, gets placed here at the second Lagrangian point. During that time, from Earth, we look for a suitable target, measure or compute the interception point, that the place where Comet Interceptor can reach. It's between 0.9 and 1.3 astronomical units from the sun within the ecliptic plane, more or less. Compute an intercept, pass by the comet. Depending from which direction it comes, the flyby speed can be between 10 and 70 kilometers per second, which is a challenge for the instrument. And then the subprobes are deployed, and B2 will venture closest, and the spacecraft A at a safe distance of about 1,000 kilometers. Yeah, and that's it, basically. Thanks for your attention. That's basically, once Comet Interceptor is done, what can we do next? Yeah, Comet Halley is going to be back in 2061, I see. Okay, thanks a lot, everyone.
Thank you so much for this really nice talk. We had a lot of facts and interesting findings. Is there any question? Maybe I start with the students.
Okay.
It's on.
Okay. So thanks for the super nice talk. I was wondering, like, for what I understood for this last part of Comet Interceptor, you can use like these instruments just for one target. So at a certain point it will like decide the target, but you cannot not like reuse your instrument for another target in the future.
Yes, so this will be true for the subprobes for sure. Whether we can fly by, well, I hope nobody from ESA is here because they don't like to hear that. Basically, the main spacecraft, if there's fuel left, there should be the possibility to maybe do another flyby, maybe. But it also depends on, you know, of course, if the environment is too dusty and the spacecraft loses lots of instruments, then there's no point in doing that. But that's rather unexpected. So I would guess that if a suitable comet comes by, we should. But yeah, well, we need quite a bit of fuel. That's the other issue. And we, as long as we don't burn all the fuel because we are too late to reach the first one, then there should be the possibility to, yeah, fly by another object. But maybe it's not going to be that exciting because to have the luck to have two objects that are dynamically new, or even an interstellar object, that would, yeah, stretching the probability quite a bit. Yeah.
Okay, thanks.
But the subprobes are lost. Yeah.
So I hope I get this right. But Rosetta found that the H2O isotope ratio doesn't fit to the Earth.
Yes.
Water. So do you expect it for those objects you want to visit to be the isotope ratio to be different?
I guess not. I mean, up to now, comets, all the comets that have been, from which we have a D/H ratio, they are either Earth-like or above. So if you take an average of all over the comets, we haven't found a comet yet with a D/H ratio that's lower than Earth. So if you mix this all together and you dump it on Earth, we should have a different isotopic ratio. On the other hand, it looks like that, and I couldn't not get to that point, but that possibly parts of the terrestrial atmosphere is of cometary origin. And that about 20% of the xenon is of cometary origin. And if you take the relative abundances in the comet, you would see that you only get through impacts, if you get that xenon to the Earth, you only get about per mil or 1% of the water from comets. So it makes almost no perceptible impact on the D/H on Earth. On the other hand, you will get a lot of organic material to the Earth, much more than the biomass if you compare just mass-wise. Yeah, doesn't mean comets bring life, but organic molecules and a lot of them. So thank you. Questions?
For my review, I have an amateur question, maybe. What is the mechanism responsible for formation of these nice spiky structural jets we used from the surface? So particles seem to have a kind of directed initial speed, which this is not the operation.
Yes, that's quite a debate. It seems like it also a lot has to do as to from which direction you look at it. So when you turn the nucleus, some of these filaments are actually not that constrained if you look from it. But if you look from it, look at it from the right direction, it almost looks like a very thin filament. It's quite a discussion as to why it looks so pointed. There are numerical Monte Carlo models around that show when you release dust and gas at the same time that the gas through collisions starts to divert much faster and basically entrains the dust flow, funnels the dust flow with it. But yeah, probably is.
Impacts probably unlikely.
Impacts are unlikely. The comet looks very much like pestered or through with craters, but it's actually not craters. These are all erosion features. What you can have is, for instance, cliff collapses. So so that stuff falls down a cliff because the object, of course, has very different heights. And so cliff collapses can also lead to spewing out material. One of the theories was like you could have some sort of a pressure cooker where you have the highly volatiles like carbon monoxide, CO2, from which you have quite a bit, building up internal pressure and then leading to a release of the material. Yeah.
It's so stable, huh? You see this.
It's so stable, yes, yes. And sometimes, I mean, there has been dust activity seen on the night side when actually the surface is in the darkness, but maybe it just got into darkness. So it's a complicated behavior.
Other questions?
Also, regarding the deuterium to hydrogen ratios,
Yeah.
as you said, that there are some known now from some comets, and they are all different than, for instance, the Earth's ocean, which is more chondritic. When I remember.
I have a slide for this. Yeah, you see the known comets here. I didn't show this slide here, but you see the D/H ratio with blue is the terrestrial.
What is the reason for these differences
between the comets?
Yeah, yeah.
I think the latest theory is that the comets have formed, or the material in comets is inherited from previous day or from early on in the solar system, and depending on where they formed, this is a cold temperature effect. So the colder you go, the more the higher the D/H ratio. So that means that these objects formed over a wide range of heliocentric distances. And as you see here, where you find the comet nowadays, let's say in the Oort cloud, you see a big variation. It doesn't necessarily mean that the comets that you find nowadays in the Oort cloud, that they also formed in the same place. But they got formed in different places, and then everything got scattered around, and it's not indicative where you find them today is where they originally formed. Also here, I mean, obviously Jupiter family comets, yeah, the range is quite dramatic.
Okay, thanks.
I think we still have a bit of time, so if you have another question.
Yes. Thank you very much for the talk. I was curious, for the Intercept mission,
Mm-hmm.
what would be the dream target? So what would be the properties, if you could choose them, what would you?
Well, you see this, there will, you know, I see some fights on the horizon with the camera team. And of course, for me, the dream target will be an interstellar object, because nobody has ever visited an interstellar object. And then, of course, it has to be active, because the mass spectrometer, if the object is not active, like the Oumuamua, which was an interstellar object, but more or less inactive, you know, there's probably no point in even switching on the instrument. But of course, the camera team on the other side, they will tell you if there's no activity, we get the sharpest images from the surface. So let's go there. And of course, you can never pass on an interstellar object, and then maybe get the chance of, you know, maybe go to a second target. But of course, if I were to choose, yeah.
Does size matter?
Size matters in terms of distance that you could fly by the object, because the pointing has some issues. You cannot get too close, because you want to have the object within the narrow angle camera, and also for navigation.
I just wonder, it must be a nightmare for the people who design the instrument to go to a target which you don't know yet. So
yes, yes. So
you must be very flexible.
You must be very flexible. So the camera system has a periscope. Well, the idea, well, maybe I can show you the spacecraft again. The spacecraft has, you don't see the periscope here. No, you don't really see it. But you have the dust shield here up on front, and so this always has to point in the direction of flight, because you have to have the dust shield that protects you. And then the camera has a periscope that will follow the comet. So as it passes, you pass by the comet, you fly through the dust or the gas, and the object, because the motion of the spacecraft is so much faster than any dust or any gas, it's basically you just have to have the shield in the direction of motion, and then you follow the comet. And actually steering this and pointing has quite some implications. The accuracy when you get pested by dust grains and the spacecraft tumbles. For the mass spectrometer, it's a big issue is the thermalization that happens in the thermalization that happens here in this antechamber, because you fragment a lot of the molecules that enter here. And but there's basically no way to fly an instrument, let's say, with where you have a magnetic deflection, because when you fly by at 10 kilometers or at 70 kilometers per second, the instrument size would have to grow by a factor 7. Because we don't know the velocity, we cannot, we cannot accommodate all the speed. So that's why we have to have the gas thermalized to begin with.
Maybe one very last question from me. Very short.
Thanks for the talk. Yeah, I have one question to Comet Interceptor.
Mm-hmm.
So what do you expect, how long will the Comet Interceptor be parked in Lagrange 2 until an object will pass by? So what is actually the probability that an interesting object will come?
Yeah.
Because you cannot stay there forever, I guess.
No, it's 3 years. And the 3 years is due to financial aspects, because you have to have the team.
So you have some emergency plan? Or
we have backup targets, and depending on when the time of launch is, you may go to a different one. But these are, comets that we know. These are short period comets, and so they are maybe not exactly the most interesting ones. But basically, we have 3 years. And there are estimates around, and I hope these estimates will improve as soon as the LSST, the Large Synoptic Survey Telescope, or Vera Rubin telescope will produce lots of data. And when when these objects are detected, so that and what the probability is that we can intercept them. I think some of the numbers I remember are on the order of dynamically new comet is maybe 30–40%, and an interstellar object is in the few percent probability. Because you don't only have the object, the object doesn't just have to, to be detected early enough. It also has to match or pass through the ecliptic between 0.9 and 1.3 AU. So there's quite a bit of limitations.
Final question. It's about the pristinity of the object.
Mm-hmm.
You said best would be a pristine object, but where do we know that? Or related question, when we have, say, Halley, I think it's probably you said 3 times. Where do we know from how often the comet was already here? So I think there are some comets which do this very regularly, right? So
yes, so Halley has been in the
ice left, but
yes.
Or you said 50%, but that's probably also depends on.
It depends on how often it passes by. Yeah, it's basically well, the idea is to get this out of the orbital parameters. If it's for instance, a hyperbolic comet or so. Halley has been in the inner solar system for thousands of years, many times. There is also, when you look at 67P, this surface, which looks like cratered, is all due to erosion. It has been in the inner solar system since 1951. It was a close encounter with Jupiter, so I think 7 or 8 perihelion passages. I don't have the picture with me. There is a picture of this, the New Horizons mission, which flew by this Kuiper belt object, which looks much smoother on the surface. So, but yeah, I guess none of these objects are really pristine because they're exposed to galactic cosmic rays, at least the surface for the last 4.5 billion years. But at least they have not seen the amount of erosion that we see on 67P. So ideally, also the pictures, the images of the comet should give us some indication as to how pristine the object really is. And even an interstellar object, maybe it formed in another solar system, may have even passed another sun before visiting ours, so we don't know.
Okay, let's thank the speaker again for this really nice talk. I just